Hello, and welcome to T9's preliminary design review presentation for the summer 2019 semester of the NASA Low Space Mission Concept Academy. Our probe is TELEPHASSA, which stands for Titan Environmental Liquid Elemental Physical Atmospheric Spectral Sonar Analysis. Our team is made up of a mixture of different types of scientists and engineers with various backgrounds. Having a team with such a wide range of experiences and ideas proved to be very useful when tackling the design process. We opted to divide the team into different subsystems, which include science, engineering, and budget. By creating these smaller teams, we were able to work more efficiently and communicate more effectively. Unfortunately, not all of our team members are able to attend this presentation, but we couldn't have completed this project without their hard work and dedication.
When designing our Titan probe, we were given a number of different mission requirements. They include a budget of $350 million, which categorizes TELEPHASSA as a discovery-level mission, a mass limit of 400 kilograms, a volume of no more than 8 cubic meters, a list of mandatory equipment that includes a propulsion system, a high-gain antenna, a multi-mission radioisotope thermal generator, or MMRTG, and of course, a heat shield. A descent system designed for a splashdown landing was also included, and a general ability to withstand the extreme environmental conditions found on Titan. Focusing on meeting these requirements, our team determined our ideal landing zone.
We chose to land in Kraken Mare because it's Titan's largest hydrocarbon sea and provides a safer landing target when compared to other potential landing zones. It also allows for a greater area for our probe to explore and characterize throughout its lifespan. The targeted region of Kraken Mare allows for the most margin of error in our descent trajectory without sending our probe into the shoreline or any islands. Our target coordinates are 49 degrees east and 70 degrees north, and the landing area has been broken down into 3 different zones around these coordinates. The blue zone allows for the most deviation during the descent, the yellow zone allows for half of that deviation, and the green zone allows for half of the yellow's deviation. The largest zone has a total area of about 16,000 square kilometers, which allows for a maximum deviation of roughly 3 degrees longitude and 1 degree latitude in either direction from our target. The red outline depicted is the shoreline, and the transparent red areas are potential hazards for landing, such as islands. With our landing zone in mind, our science team worked together to determine our scientific goals for our mission.
Our science goals consist of primary and secondary objectives. The primary objectives include the goals that directly deal with characterizing Kraken Mare, while the secondary objectives are other types of useful science we were able to add in around our main goals. Our primary objectives are to determine the chemical composition of Kraken Mare, with an emphasis on trace organic compounds that could potentially support present or future life forms. In addition to chemical analysis, we want to investigate the depth and morphology of the seabed and examine liquid columns in Kraken Mare to determine if chemically stratified layers are present. Our secondary objectives include obtaining meteorological and atmospheric properties of Titan during descent and surface operations, and to collect images and ambient sounds both during descent and after landing. While each of these individual goals are useful in their own right, they can be more valuable when examined as a whole to provide context of the conditions for when the data was collected. Now let's take a closer look at the scientific payload of TELEPHASSA.
TELEPHASSA contains 6 key scientific instruments. The sample analysis at Titan is based on the Curiosity's sample analysis of Mars and will be modified to include a liquid chromatograph. We'll also remove the bulky evidence sample wheel to help conserve mass. We've streamlined the sampling process through the use of SAT's sample suction tube, which is capable of extending down into Kraken Mare at various depths. In doing so, SAT is able to test the chemical composition while also exploring the possibility of stratification. The multi-beam sonar will survey the seafloor topography with multi-beam imaging to map Kraken Mare's seabed and calculate its depth. The atmospheric structure instrument and meteorology package is a suite of sensors that will analyze meteorology and atmospheric data during descent and while on the surface. Its goal is to calculate atmospheric density, temperature, pressure, wind speed, and direction. The full-sphere multi-camera systems of the descent imager are designed to capture sweeping panoramic views of Titan during descent as well as landing. The panoramic camera will take a series of photos in a 360-degree arc around the probe using 2 cameras to gather images of the Titan oceanscape. The microphone will passively record its surroundings to gather Titan's soundtrack. With these scientific instruments in mind, the scientific team handed off our work to the engineering team for them to start integrating the payload and to design TELEPHASSA.
During the process of the engineering design, multiple factors were considered when deciding how the payload will be organized and designed. Such factors were the position of the components, including the instruments, antenna, MMRTG, rudder, raft, airbags, heat shield, and air shell on the probe, which would maximize the efficiency during the entry, descent, landing, testing, and communication with Earth and the orbiter on Titan. The engineering team also made decisions on the type of materials utilized in the construction of the instruments and the other equipment in order to be able to withstand Titan's atmospheric and surface conditions. In addition, the power supply for the entire probe determined the size, capacity, and power source used in TELEPHASSA's design, along with the basis for the team's calibration, as well as specifications on all instruments, which will ensure the instruments are accurate when measuring on Titan to assure there will be little to no error in data and results. These factors guide the engineering team's design of TELEPHASSA.
In the top left corner of this which shows the instrument configuration during descent. The PanCam, the descent imager, the high gain antenna, and the meteorology package are retracted to ensure stability and to improve center of gravity during descent. In the top right corner, you can see a wireframe view of the probe, indicating the location of the MMRTG within the probe. In the bottom left corner, you can see the bottom of the probe in its final experiment-ready phase. The instruments shown in the order of the label points are the multi-beam sonar and the propulsion system. In the bottom right corner, you can see the top of the probe in its final experiment-ready phase. The instruments shown in the order of the label points are the atmospheric structure instrument and meteorology package, the high gain antenna, the sample analysis at Titan, the rudder, and the flotation raft. Based on these configurations, the engineering team had completed the final design of TELEPHASSA, and the entire team began planning the timeline of the mission.
Shown now is the estimated timeline of TELEPHASSA's assembly, testing, launch, transit, and landing. So in 2019, with the selection of TELEPHASSA, we expect to engage in a massive social media campaign to generate publicity and to inform the general public of what our mission is and what its scientific goals are. We expect to start cutting metal of TELEPHASSA in 2021, and in 2023, we expect to finalize instrument selection and testing of all the instruments. We expect to start installing instrument in 2025 and expect installation of the instruments on TELEPHASSA to be completed in 2027. In 2029, we expect to start extensive testing, which will include thermal vacuum testing and environmental testing to ensure that TELEPHASSA is able to survive in the extreme Titan environment. And then finally, in 2031, we expect TELEPHASSA to launch from Cape Canaveral, Florida, and begin its 8-year transit from Earth to Titan. And then finally, in January 2039, we expect TELEPHASSA to arrive in Titan, where it'll engage in detailed scientific analysis. At first, it'll go through the atmosphere and collect detailed atmospheric data, and eventually it will splash down into Kraken Mare, where they'll be able to do detailed chemical analysis and scientific analysis of the lake, as well as the surroundings, and as well as snap detailed panoramic photographs of the region. We expect the mission to go on until 2046, where we expect the TELEPHASSA's radioisotope generator to run out of power, but we will make every effort to ensure that TELEPHASSA can run as long as possible to ensure a maximum mission success rate.
And with that, our team would like to thank the Space Mission Concept Academy for this amazing, amazing opportunity to learn and grow as scientists and engineers. We all feel we've grown substantially, both as individuals and as a group, and certainly improved our abilities to work within the team setting. Thank you so much.